well, in Greek.
Yes.
Well, I'm not going to LaTeX it for you now. So.
No.
I can write it on the board. So it's like this. That's a vote. But the passport authorities decided that there should be one-to-one transliteration in the Roman characters, right? So I get the GK here, which makes absolutely no sense phonetically. So my academic pseudonym doesn't have the K. I don't use it. Anyway, so much for the substance of the talk.
I'm ready for it, but then you have it here.
Yeah, well, I don't know, it was,
Just do your talk.
he's gone.
Just do your talk about the transliteration of Greek.
Yes. Okay, so it's going to be a high-level talk. I'm not going to drill down very much. I mean, there is detail, but I'm not going to focus too much on one particular thing. It's mostly an overview of work I've been doing last few years. It's all related to verifying programs. So it's about program verification, and in particular programs that use the heap in a non-trivial manner. So programs in languages that that use pointers, object references, and do so in a way that is important. Okay, so just a very kind of general slide about why verification is hard, as in theoretically as well as practically. So if I gave you some code that computes the square root of some number, what does it mean to verify that, right? What does it mean to specify it, to write down the intended behavior? What does it mean to sit down and construct a proof that that code is actually correct or incorrect? Either way. That is already a difficult problem, so there's all sorts of sources of undecidability, intractability that are going to go into them, right? As we use first order logic, we use numbers, we use real numbers, we have imperfect computers with finite precision, we have numeric errors and so on. I'm not going to even talk about all these things, right? It's just that to set the background that already verification is hard, okay? And like I already said, just writing down in a formal way our expectations for this code is difficult, and it's also easy for us to make mistakes, and that happens very often. When we write down specifications, we very often make mistakes. And that is, by the way, this is partly an objection to formality. Okay, so if we can't even formalize in mathematics the things we have in our head, then we shouldn't, hold the formality too high. Anyway, now, so assuming we've done that, then working out what this code does at that same formal level of our specifications, so that I can actually compare or contrast, is also hard. And doing so automatically is even harder. Okay, so it's one thing for a human to look at the code and say, okay, x is equal to x plus 1, therefore x increases by 1, whatever. But it's even harder for a program to do that. Write a program that takes this program as input and outputs the specification, the specification of what that program actually does, not necessarily what we intended to do. Okay? And of course, even assuming we have done these two steps, comparing is also, generally speaking, undecidable, right? We're going to use some formalization language that will have undecidable problems of entailment or satisfiability and so on. Okay, so all these problems are generally hard. Nice pessimistic slide to start the talk with. Now, why that was general, and it's not so much related to this, to the kind of hardness I'm interested in. I'm interested in the heap. So let's look at the program that does stuff with pointers. No arithmetic whatsoever. Take a piece of paper out and tell me what this does. Okay, I've left the procedure name here in, I didn't obfuscate it. So that should already spell out half of the specification, right?
Reverse the link.
Okay, reverse a
Link.
linked list, okay?
Yeah.
But do so in place, okay? By the way, so we're not copying the list so that we then reverse it or stuff like that, right? We actually do some pointer surgery and never allocate or deallocate any memory. We're just doing it in one pass and we're flipping the pointers around. Okay?
Yes.
That means that at any given point we have the list we've already reversed and the list we have to reverse. Okay, so this is the kind of shape that would, we have all these points are structures of type node. Okay, and these structures of type node have a field called next, which is what is the pointer that tells us what is the next node in the list. And basically, while we're running that while loop, we will generally have a shape of this form. Okay, the bit we've already reversed and the bit that still remains to be reversed. At the end of the algorithm, obviously, everything is going to be pointing backwards. Okay, so that's. So, like I said, not easy to figure out what this does just by looking at it. How can it go wrong is another question. Okay, so, one thing is that it might actually not reverse the list. Another thing it might do is it might crash because it tries to access unallocated memory. Okay, it might leak memory because it leaves out, say, one node, that detaches it from the list and makes it unreachable from the program state. Okay, that's called a program memory leak. So there are many different ways of this going wrong, and some of those are specific to pointers, specific to programs with pointers and the languages that allow pointers, or object references, or whatever you want to call them. I don't want to go into garbage collection right now, but so that's another thing. I don't remember what's on this slide. Okay, yes, pointer arithmetic. I'm not even talking about pointer arithmetic. So, does anyone know what this thing is? It's a very interesting data structure that is created by people who like to make other people cry. It's a doubly linked list, so you can go backwards and forwards, but it only has one field, one pointer. It doesn't have a back and a next and previous field. It has just one thing. And how do you use that one thing to obtain the address of the next cell? You XOR the previous pointer with this one, this value here, and you obtain the next. If you wanted to go backwards, you have this address, and you have this field, so you XOR them together, and you get this one. Okay? Saving memory is the name of the game here, so this is for embedded systems, okay? But this is an actually used data structure, and it obviously uses pointer arithmetic on the.
Doesn't it just fail occasionally?
Yeah, how is it?
Everything fails occasionally.
No, I mean,
If you use it properly, then it doesn't. Because the idea is that you can always recover exactly, if you have the two things, you can always recover the third by the properties of XOR. That's the whole point. Yeah? So, as long as you keep the beginning and the end of the addresses, you can always traverse that doubly linked, or double-ended, I should say, as well as doubly linked.
But does this cost more time?
Of course. I suppose it depends on the processor, but I'm not even gonna go there, right? I mean, I just put this up to say there are even worse monsters, and I'm not gonna talk about them because we're not even near. I mean, there have been some attempts to verify this kind of thing, but they are token attempts, I should say. They're very specialized to this.
So to teach this to our first year students.
Mm-hmm. And then, yes. Anyway, so focusing a little bit more, within the kind of formal verification field, there is what is called program analysis and shape analysis. So program analysis are algorithms that try to focus on proving one individual property as opposed to, say, functional correctness of some code. The idea is that you give them some code and they come back and prove a small theorem, as they say. So they will tell you, oh, this code doesn't, I don't know, divide by 0. I don't know anything else about it, but I can tell you it doesn't divide by 0. Okay, so we kind of make the problem easier by focusing on smaller safety properties. And these are examples of other properties, throwing an exception, assertion failure. They don't necessarily, they're not necessarily theoretically easier, these properties, because you can usually produce some program transformation that turns one property into the other, right, for any pair of these. So it doesn't actually, it doesn't make the theoretical problem easier. It might do so practically. But whilst we have made it a bit easier, we are going to make it harder by requiring that it's fully automatic. Okay, no hand proof, no input, or at least minimum. Okay, we're not going to ask our lowly trained programmers to write down mathematical specifications for our code, nor to be kind of nursing the program analysis algorithm while it's running and saying, no, do this, do that. Okay, so shape analysis is one particular kind of program analysis that focuses on memory safety. So programs with pointers and the problems that are specific to that family. So accessing unallocated memory, memory leaks, double free is another one I failed to mention. So if you're in a language like C, you can free something twice. You can free a pointer twice. No, you shouldn't. Don't do that. In other languages that's okay, but in C, which is used in a lot of software that's running on actually critical systems, that is a possibility and you don't really want that to happen.
So what does that mean by freeing twice?
So you deallocate some memory twice. You have its address. Yes, the same block, same pointer. You say, you tell the memory manager, I don't need it anymore, you can recover it. But then, by mistake, you do that again.
Okay.
The standard of C says, a nuclear missile may launch if you do that. Non-deterministic behavior immediately. It might, you might actually get a nice runtime crash message by your runtime saying you tried to do a double free, or a nuclear missile may launch.
You may already have freed that bit of memory, so it's loose.
Yeah. Anyway, so that takes us to separation logic, and now I'm going to start talking a bit about the logics that are used in building these analyses, shape analysis and program analysis. Let's see. I'm going to more or less assume that everyone knows about first order logic, or to some degree, okay? Because otherwise it will take me a lot, further back than I would be able to. So let's try to specify this shape. This is the invariant for the while loop of the list reversal procedure. Okay, so the idea is that simply we have two lists here. One, it doesn't matter that, we can even ignore the fact that they kind of start at the same point. The only thing we need to know to show the correctness of that loop, that its memory safety, I should say, is that there are two lists, two linked lists. That's all we need to formalize. Okay, so let's try to do that using first order logic. And let's suppose we also have a magical predicate that says that if A is the beginning, is the address starting a linked list, then list of A will be true if indeed there is a linked list starting at A. Okay, let's take that as a given so that we don't have to sit down and see how you can formalize that. Let alone you get outside of first order, but anyhow. So maybe we can use this, a simple conjunction. X is the program variable that goes forward, and Y is keeping the backward running list, right? So we can switch, shift stuff from X to Y. So maybe that is good enough. But here we're seeing this formula in isolation, right? We don't know what has happened before. We just know that this is the invariant for our loop. So we kind of assume that any possible state that satisfies this formula is, a possible starting state for our loop, okay? And now the problem is, what if the two lists are sharing a tail? And I'm using this as a kind of transitive closure, these arrows. So here we have X, here we have Y, here we have null. This model, this program state, will still satisfy the statement that in X we have a list and in Y we have a list, right? But if we try to run our while loop on this, we will crash. I don't want to go into the details why we will crash exactly, but clearly you're going to try to shift the pointer from here to here, and then when you get to the common part, what is, you're either going to leave something out, or you're going to, not end up with the list. So we can kind of add stuff to solve the problem. How? Well, we keep our original attempt, and then we add an ugly monster that says that basically, and use another magical predicate that we just introduced here, which is basically transitive closure of reachability. Okay, so we're saying for any address that is reachable from X and from Y, A is equal to null. Basically, the only address reachable from X and Y that is common is the null pointer. Okay? That's kind of a way to solve the problem. And indeed, this will force the two lists to be separate. But we have an ugly formula here. And we have an ugly quantifier that makes tools generally scream, automatic tools. So, what if I'm running my reverse procedure I'm calling it from another procedure that maintains a third list, right, at Z. Don't I now need to change the invariant of the while loop to say that, also Z is not sharing anything with X and Y? Okay? I do, basically. And that it gives you a sort of a complexity that is not local. Okay, so suddenly the complexity of your proving methods increases with stuff that is not actually relevant to what you're trying to prove. You're looking at this procedure in isolation, and suddenly something from very far away becomes an obstacle, and obviously your performance will just deteriorate to nothing as soon as you have 10 variables, right? Because you're going to make these monsters of formulas. Okay, so this is why first-order logic isn't very good at reasoning with, about transitive closures and stuff like that. And this was the the beginnings of new attempts to start reasoning about these problems with a new logic, as opposed to trying to shoehorn tricks into first-order logic and make it work. And one of these separation logic, work done by others, by O'Hearn and the late Reynolds initially. And it's basically a first order logic, at least in its generality, with equality, and a few added trinkets. So one of these things is the atomic formula EMP, which means simply the heap is empty. There's nothing allocated. A relation or a predicate or a two-place predicate that simply says this pointer points to an allocated cell in memory whose value is, X points to Y, means the value of address X is Y, is allocated, and it is Y. The separating conjunction, which I'm going to show in the next slide, which is, anyway, it's a substructural conjunction, so it's not like a classical conjunction, it's something similar, but it is important, the differences are important. And the separating implication, which is the kind of deduction theorem relative to the separating conjunction, and I'm not going to say anything about that implication because it's just crazy and makes everything undecidable. So just ignore it for a moment. We will also throw away all the constants, all the functions, and all other relations apart from equality and this nice predicate. Okay, so kind of throw some stuff away to again focus on the shape of the heap as opposed to what
So
data.
What is this equality plus? So where is the plus?
No, there should have been a comma here. So it's first order with equality plus all this other stuff.
Ah, okay, I saw.
There's no arithmetic if,
Okay.
if that's what. Yeah, definitely no arithmetic. Okay, so I'll show you briefly some semantics. I hope that's not going to scare anyone. We assume we have an infinite set of values, say the integers. Okay, say we're only gonna I don't know, work with programs that use integers, and a strict subset, but still infinite subset, is the set of addresses. Okay, so say we have the z, the integers, and only the positive integers are addresses. Yeah, just fix something like this, and assume that 0 is never allocated, because that's going to be a null pointer, basically. Okay. Then we use something called a stack or a store, which is a very old invention, and it's basically something that interprets program variables. So it takes a variable and it tells us what value it has at a particular program state. And we also fix that the interpretation of this constant is 0. Just just standard stuff.
So sorry, that's just asking, it's the same as the value of whatever.
X. So if you have a program variable x, s of x will tell you now at this program state x has the value 5. So it will tell you, give you 5 back. Okay, so it just interprets the program.
X is an pointer.
So you have sorry, I should have said this is a set of variables, all the program variables and more, because you may need logical variables, whatever, it doesn't matter. So it's just a function that assigns values to the variables you have available. So S is going to be a part of the program state. Okay, the stack is part of the program state. And the other bit of the program state that we're basically adding, because this is a standard first order evaluation. Okay,
So
what we're adding, yeah?
usually stack means some kind of order, right? I mean, or
Right, okay. If you add procedures,
yeah.
then the stack becomes the kind of the stack frame or that kind of thing. That's where the terminology comes from. You can call it the store, as some people do, just to ignore that bit, that kind of meaning of the word stack. And what we're adding is the heap, which is basically a finite. It's a function whose domain is finite. Okay, and its domain is some addresses, 2 values, and I've allowed here tuples of values by putting this star, because if I have a struct that has I don't know, some next field and some x and some y field, then I'm just going to model that as a tuple with 3 elements, next, x, and y. Just to make things simple. It's so that we never ever have to do pointer arithmetic, right? Because otherwise we would have to resort to that. So that's the heap. Now it's important to say that, to remind that this is going to be a finite function, right? Our address space may be infinite, but any given heap only ever has finite memory allocated in it. The Boolean connectors as usual. And this is the satisfaction relation. So a model now is going to be a pair of a stack or a store and a heap. And it interprets quality only using the store. Okay? So if you want to decide whether this program state makes x and the variables x and y equal, you just look up those values and you just compare them, okay, using the store. It's kind of a very trivial thing. Now, M is going to be true if the domain of the heap function is empty. So in other words, nothing is allocated. Again, very simple. Now, here comes the first interesting bit. So x points to the tuple y. If the interpretation of x is some value u, the interpretation of the tuple y is some tuple v. These are sets of values. Then, I mean, all these are values. Yeah. And if I pass u through the function h, I get back exactly the tuple v. Okay? Yeah? And finally, and that's very important, typo, the domain of h is a set that only contains u. Okay, so nothing else is allocated. Okay, so x points to y means our heap is a singleton. Doesn't allocate any other cell but this one. Yeah? Okay? It's sort of not monotonic, if you like. Okay, it will only be true on heaps of size 1. Okay, now the star, the separating conjunction, is interesting. If this were a model logic, and you can see it as a model logic, the star is a diamond modality, so it's an existential modality. Okay, so it's true if there exists two other heaps, HA, HB, such that their domains are disjoint. Okay, so the two heaps don't contain any commonly allocated addresses. Okay, so the addresses that HA allocates and HB allocates are disjoint. And if you put these two heaps together, you get back the one you started with, H. Okay? So it's basically saying, can I split H into two parts, such that, disjoint parts, such that the first one with the same store satisfies the left formula and the other one satisfies a typo. That should have been B here, not sigma B. Okay? So it's an existential modality. It says, I can split my heap in one part that satisfies A and another part that satisfies B, and these two parts are disjoint. And just for fun, I'm gonna show you the separating implication, which is basically saying A magic wand B, because that's kind of a cute name, if for all heaps HA that are disjoint to H, okay, so all the heaps I can safely add to H if you like, and there won't be any clash. Oh, and I've missed out something out here. It's full of type. Okay, so all the heaps that do have this property and satisfy A, then if I put those together, so the one I started with plus this extra one that satisfies A, I get B. Okay, so it has this kind of implication feel, because it says if for some worlds something happens, then in this world something else happens. Okay, but it is a modal implication. It's a substructural modal implication. But like I said, don't worry about it too much because most of the time we're going to ignore it. And finally, quantification. I'm just going to show the extension quantifier. It's exactly like first order. It's just that we only ever switch. Change the stack, right? Quantification doesn't touch the heap. So basically, there is XA means that there is some stack S prime that agrees with S in everything but X. So all the other program variables get the same valuation, but X can non-deterministically assume some new value. Okay? And then the resulting model S prime comma H satisfies the formula, but without the quantifier now. Yeah? Okay, now I'm going to show you some sample
Look at
facts.
the previous
Yeah.
slide. And there's no relationship between the connectors.
There is, but it is a sort of deduction theorem one. So if A star B, so that's kind of equivalent to that.
Okay.
It's like the deduction theorem when you replace these with conjunction and classical conjunction and classical implication.
And there's no negation.
There is negation. In the full separation logic, there is negation. I'll here, and the negation is as usual. But I won't really talk about negation because all the tools ignore it. So yeah. Okay, I'm going to show you some sample facts just because they are often surprising to people. How much time do I have?
You have until 4, so you have hours.
Okay, yeah, but I don't want to kill you. Okay, so empty doesn't imply X points to A, right? Because empty requires that the heap is empty, and X points to A requires that the heap is exactly of size 1. So the one cannot entail the other. Okay, so far so good. The other direction is also true, right? Because, and this is again the non-monotonicity, I suppose, of these points too, is that if you require the heap to only have size 1, then it cannot be of size 0, because emp really doesn't take any prisoners, right? It wants the heap to be of size 0. X points to A doesn't entail X points to A star X points to A. Okay, and this is why star is a substructural connective, right? It's like linear logic, where you cannot repeat things. Basically, this is saying I can split my heap into 2 parts, none of which is empty, right? At least, you know, they both will have size 1, and also neither will be empty. But this one requires that the heap will have size exactly 1. Okay, so you cannot split it into 2 non-empty parts. Okay? Starring, or rather saying, so this is the kind of dual to that to this statement, saying that I have a model, I can split it into 2 non-empty heaps, okay, but they are not disjoint because they both allocate address X here. One allocates X, the other one allocates X. Okay? I cannot put them together in a disjoint manner anymore, right? So this is just unsatisfiable. There's no model that satisfies it. And another example is that if you have X points to A and Y points to B, so 2 cells allocated, and I can split my heap into 2 and everything is fine, this necessarily requires that X is not equal to Y. Because if X were equal to Y, then I wouldn't be able to split my heap in 2 at all, to begin with. Okay, so this entailment is true. Here I have just repeated the same thing, right? So just by identity, you know, it will be, that's going to be okay. But the other added bit of information is that X is forced to be not distinct from Y. And finally, this is just a recap of the stuff. Here is basically the dual of that, is that if you have 2 addresses in your heap, you don't have exactly 1, you have 2. Okay? So it's just the interplay between the points 2 and the star is important because this is not a first order kind of thing, right? If you replace the star by classical conjunction, then you get the exact opposite. So if you say my heap consists, and this is classical, note